Hello everyone, I'm really glad you could join us this afternoon. My teammates and I are extremely excited to share with the world what we've been working on for the past 2.5 months for our synthesis project. Our project is called SciPOC, Semantic Classification of Indoor Point Cloud, and it uses deep learning at its core. We did it in collaboration with both Esri and the Dutch National Railway Company, the NS. Now, before I begin talking about the project itself, let me introduce you to our team. During this presentation, you'll get to hear each and every one of us. Firstly, we have our project manager, Mels, who has coordinated the entire project. Our technical leader, Jai, who has always made sure that the technical aspects of our project were on point. Our quality analyst, Dida, who has strived to double-check everything and who ensured the continuous quality of our deliverables. Our product manager, Shawai, who has made certain that we were doing what was required by our mentors. And last but not least, myself. I handled the communication with the outside parties all throughout the project. Of course, regardless of our predefined roles, we all work together side by side to make this project a success. Now, this is our research question, which encompasses the main essence of our project. It may seem like a very academic formulation, but what we were basically asking ourselves was, in very non-technical terms, can we teach a computer to recognize various elements from an indoor environment, such as furniture or vending machines, or plenty others? Of course, you'll find the answer to this question in a bit, but for now, we need to mention the most important element of our project, and that is deep learning. Deep learning has been our main tool, which we have used all throughout the project. What is deep learning exactly though? It is a mechanism which is used for training deep neural networks. These are neural networks which contain a number of hidden layers. A deep learning algorithm does it all by itself, unlike a machine learning one, in which a developer may intervene. Our features are also automatically learned by the network, which in turn makes it a bit more robust than a machine learning algorithm. Now, of course, there are lots of things which can be mentioned about deep learning, but for the time being, we would like to tell you more about the project itself rather than the theory behind it. Should you be curious to find out more, we invite you to take a look at our paper, which will be online on the TU Delft's website pretty soon. There, we also provide more background information as well as external resources we will introduce the reader to the world of deep learning. For now, though, I will give the spotlight to my teammate Jayu, who will tell you more about the first part of our project.
Thanks, Alex. As we know, a point cloud is a set of points where each point is a vector of its 3D coordinates, and maybe with additional features. These points often contain rich information, but they are unordered and is topically distributed in space, which makes it really difficult to handle for a typical convolutional neural network. In this project, we explored the possibility of several neural networks as listed, named PointNet and PointNet++, PointCAN, DGCAN, SuperPoint Graph, and VoltNet for indoor point cloud classification. These networks vary in their designs, but here we will not dive into the details of them. We will, however, take a closer look at how PointCAN works, because this network was eventually selected by us for the case study. As we said, the point clouds are unordered, so if you look at the convolution inputs for regular grids and for the point cloud as shown in the figure, by following orders as illustrated, the convolution operator for the second, third, and fourth scenarios could be computed as shown in the first equation sets, respectively, which means that a direct convolution will lose the shape information while carrying about the orders, which is undesirable. For PointCAN, a k times k dimensional X transformation for the coordinates of k input points is learned with a multi-layer perceptron. This is called the XConv, and it is the building block for PointCAN. The XConv for these scenarios can be formulated as the second equation set, respectively. As you can see, with an ideal X transformation, the XConv is capable of being invariant to the ordering. In regular grids, convolutions are recursively applied on local grid patches. Similarly, with point clouds, xconv is recursively applied to aggregate information from neighborhoods into fewer representative points, but each of these representative points has richer information. We used the Stanford large-scale 3D indoor spaces dataset to evaluate the performances of these networks. The dataset is split into 6 areas. We trained the neural networks on area 1 to 5, and we used area 6 for evaluation. The evaluation result shows the point CNN and the superpoint graph are most competent. While considering the superpoint graph needs a lot more pre-processing and complex configuration, we therefore select the point CNN for the case study implementation. Next, Miles will take over and introduce the case study on the NS dataset.
All right, thank you, Zayu. During the project, we got the opportunity to work with the data provided by the NS in order to test our research in a real-world environment. They wanted to look into the opportunities that deep learning would provide them when using this on the scans they performed in their stations. For our case study, we focused on Amersfoort Central Station, which can be seen on the screen. We did this with the aim of labeling the points in the currently unlabeled RGB-enhanced LiDAR data with a class code showing the identity of the point. This would allow for this data to be used in all kinds of applications, such as in asset management on stations. The benefit of a network is that it is a fast and automatic process and reduces a lot of the manual labor, potentially saving hundreds of man-hours. As the data was unlabeled, so unfit for training, we needed to do all of the labeling for our experiments ourselves. This meant looking at the scene and labeling objects such as entrance gates and information signs. In total, we distinguished 18 different classes, which we all labeled using RTS Pro. We first converted the 19 different scans we acquired into the LOS format and then merged them together into one before splitting them into smaller regions with a 5x5 area, as can be seen on the right, for more efficient processing. Now we'll show a short demo of how this labeling process went in practice. With an ArcGIS, you first add your data into the map like this. Then, as we are pretty far away, we zoom to the layer and change the visualization to RGB to get a better view of the scene. Then, we can rotate the scene and look for the object we want to label. In this example, we take this yellow egg. We then rotate the scene once more to make it easier to create a profile viewing, which zooms in on the data for easier selection of the unwanted points. In the profile viewing, we then get a good angle to see the object of interest and select it using the Select tool. The selected points, shown in blue, can then be labeled as the class we want, which is 1 in our class code structure. To see the change, we can then take a look at the statistics of the loss file, where we can see the class code of 1 now as entries, or we go to the symbology again and set the visualization to classification, where we can modify the color for the class we see, and we can see which points are labeled as which class. As we have talked about preparing the data, Gita will now explain the experiments we have done during this project.
Thanks, Miles. Okay, now we have labeled point clouds with 6 different objects, which are yellow eggs, garbage cans, couches, entrance gates, ticket machines, and vending machines. We separate them into training, validation, and testing, and we train for about 6 hours. Here is the initial result. We can see from the graph that our training cannot converge. And from the evaluation, we can see that almost all points are classified incorrectly. So why is that? Here we can see clearly that we have unbalance between labeled and unlabeled points. More than 90% of our points are still unlabeled, and that may cause the training cannot converge. Besides, the geometry of many objects are not fully scanned. So based on these initial results and feedback from our mentors and clients, we try another approach. Here we cut our bounding box, so we have a smaller scenes now, and we relabel them by adding new classes, which is floor and other classes. and we clean the dataset by removing people, floating points, or other clutters. In this experiment, we didn't separate the training, validation, and testing because we only want to see whether we can get some results. And here is the results. Now we have a high similarity between prediction and ground truth. From this experiment, we get the overall accuracy around 0.9 and mean IOU around 0.8. And from this training, we apply the training model into a different data set outside our training data. Here we can see that some parts of couch here are classified as garbage can. Meanwhile, the floor and garbage can itself are correctly classified. Notice that we have unlabeled floor in the ground truth here. Next, we go back to our large scene. Now we apply the approach from the small scene. We add new classes, so we end up having 18 different classes, and we separate them into training and testing. We have one for training and one for testing. So here we can see that the ceiling and the floor have a fairly good result, but here when we zoom, the second floor are classified as ceiling. Here is the same result, the ceiling classified as the floor. And for the entrance gate here, we can see that the entrance gate are variously classified into different classes. So from this result, we may need more training data to get better results. Last, we try another approach based on Kudinov. We only focus on the one object, which is a yellow egg. So we collect all yellow eggs we have in the station. We have 9 yellow eggs, so we separate them into training, validation, and testing. Interestingly, by using the same parameter with the previous training, we only get the overall accuracy of 0.29. But when we reduce the block size, the overall accuracy increased significantly into 0.8. However, how the block size affect the overall accuracy still need to be studied in the future. Okay, so now we move to Xiaoai. Xiaoai will present about the web application.
Thank you, Dida. In this project, we also developed a web application for users to get semantic segmentation results in a more friendly way. The picture shows the technical architecture of this app. For the front end, we use Vue as our main JavaScript framework. We also use Bootstrap to make our web pages more responsive. 3JS is used for the 3D visualization. For the backend, we use Flask, which is a lightweight web application framework. We also use Circular3 as our database. To transmit data between the clients and the server, we use Axios to connect the front end and the back end. For the functionality of this web application, it provides 3 main functions: file uploading, downloading, semantic segmentation, and result visualization. The picture on the left shows the process of file uploading. The app requires the user to provide training datasets and testing datasets. If the user wants the process of validation, they can also provide the validation datasets. The picture on the right shows the process of segmentation. It contains 5 steps. After TensorFlow sampling, compiling, and dataset preparation, we can perform dataset training, testing, and validation. For the result visualization, we can see one good result on the left animation, since you can see the prediction and the ground truth are quite similar. However, the result on the right animation seems a bit messy due to more kinds of entities in the scene. Now Alex will give a conclusion of our project.
In the end, we would like to thank our mentors for being there for us throughout the project. Meeting up with them every Friday has been awesome, and they really helped us along the way, and they have always been available for us whenever we had a misunderstanding. We truly hope that you enjoy our presentation. Should you have any questions, feel free to ask us in the YouTube chat, as we'll be here to answer them for the next 15 minutes. Thank you.
Okay, and we are live over here. Now I can actually stay here. Also nice for a change.
Very good, and again, an impressive video. We do have some questions, and we start with a question by the supervisor of this group, Martijn Meijers. He asked the question, given that the training phase took really a large amount of time, what would be ways to improve this tedious process? Who can I give the floor?
Zayu, I think that you wanted to take this one.
I can take that.
Mm-hmm.
I can take it. Can you hear me clearly?
Yeah.
Yes.
Okay, super. That's indeed a question, Martin. Currently, I can say, unfortunately, there's no magic for us to deal with that. That's a way that we have to take for the long-time training. In our project, the training was almost done on my local PC, and it has really taken a lot of time, as you can imagine. And as you can also see, the epochs and the training time in our reports. But what we can do, as I said, is limited. But what we could do is for the experiments, we can monitor the process of training, and by logging the process, for example, we can take a look at the TensorBoard. If you are familiar with the TensorBoard, that's a GUI for us to monitor the training process. So we can see from the TensorBoard, is the training overfitting, or perhaps is the network not learning anything meaningful? So if that happens for some cases, and it did happen in our experiments, so in that case we can terminate the meaningless training early, so that we don't waste additional time. And by the way, that's called early stopping. Yeah. Aside from that, I guess our only way is to maybe change to more fancy hardware like that. Yeah.
Yeah, to tack on that, it's also one of the strengths of deep learning is that we take one time a very long approach to learn a network, and then afterwards the classification, which is actually used at the companies, is done in a matter of minutes. So it's also a method that initially takes a lot of setup time, but then in the end, actually deploying it will take significantly less time. So in that way, we don't the final product that we deliver does not take that long.
Very good. We move on to the next question, also by our supervisor, Edward Verbrey. He's asking, your client is Esri Netherlands, and so not Esri Incorporated in Redlands, USA. How do you sell your research and development to the mother holding Esri Incorporated? Should this kind of deep learning semantic enrichment be part of RTS Pro? Who are going to be the users then?
Well,
who will answer this question?
I think I can answer this question. In this project, we did develop a web application to integrate what our research part into application one. However, I don't think we will make this kind of deep learning stuff to be part of the RTS Pro. At first, we did try to make our research part into add-in in the RTS Pro, but actually the deep learning projects and the neural network setup has a very high requirements for the user computer configuration. So we do prefer a web application to integrate the research part. And I think the users, since our project is for the indoor semantic segmentation, so I think it will be useful for the users to do some 3D modeling, like the indoor objects or the indoor navigation part. So that's all.
Yeah, to tack in on that answer, so for our purposes also, our PCs had some issues with the total loading time that we have on RTS Pro, but the functionality that we have implemented can obviously be taken up and can also be integrated into RTS Pro itself. So it's more that during this project, it was not feasible for us in the same time to integrate it already. But the method that we are using can be added. And right now, they already have some automatic segmentation algorithms, such as for ground filtering and for classifying buildings, which they do on a lot of data they already have. So in a similar fashion, our code could also be integrated as an option for the users to use in RTS Pro. But this is something that's a more that we as a group of students to get that integrated into the entirety of RTS Pro, that was not feasible during our project.
Okay, well, you talked a lot about RTS Pro. There's also a question by Hugo Ledoux. I saw that you're using the open source and free software Cloud Compare to view and explain the results. And how did it perform compared if you compare it with ArcGIS Pro? Can you say something about that?
Yeah. So what we noticed also during the labeling process was that if there is a lot of data that we need to process on our local laptops, because we were pretty hardware limited during our project, then ArcGIS Pro sometimes cost too much time for our laptop to compute with it. That is also due to me not having that good of a GPU, so the visualization would run out. So for that purposes, we sometimes shifted to Cloud Compare, because in overall the total loading time that Cloud Compare needed for for what we did was smaller. So also if we wanted to cut up the data just in like linear lines, then Cloud Compare would perform better. But for all the intensive labeling applications and for the more in-depth options, and then ArcGIS Pro won by a landslide. So it's dependent on which steps we had to take. But to save my laptop during the labeling process, for validation, we often switch to Cloud Compare, because that was easier and it caused less overheating problems with my laptop. But that's also because of the, it was mostly due to hardware limitations.
Yeah. Okay, thank you very much. Then we have a question by Jos. Say that some group of people develop a tool which want to classify point clouds in near real time. Could that be done with your method, or if it's already been trained?
Yeah, so Gita, I think that this is mostly in your case because you did most of the classification in the end.
Yeah, I will try to answer. So if we already have the pre-trained model of
you're
into
yeah.
But,
I think that your
then
voice is sometimes dropping.
Oh.
Yeah.
Is it clear now?
Yeah, I can hear it now.
Okay. So for the pre-trained model, we can use the, but we need to notice that another scene having the similar, for example, we train in the one NS station, we can run the another scene of the station. But if we want to run, for example, to airport, we cannot do that because they simply having different feature.
Yeah, the training that we did on indoor scenes, it's very location dependent, because every indoor building it's different. So if I train on chairs in, for instance, a library where you have a lot of couches that you can just plop down into, and if you compare that to a bar, that's just totally different furniture, which makes this harder. But if you need focus on the location already and train on the location where you want to run it, it should be feasible.
Okay. Then we have this question by Liang Yang Nan. Did you compare your method with other existing methods? And what would be your conclusion?
Zayu, I think that this is more for your part of the project.
Maybe I can try to answer that.
Yeah.
Maybe I can try to answer that. Actually, we tried. If you see our presentation, well, we don't have it again, right? Mm-hmm. But if you see it again, in the methodology part, we actually compared 5 or 6 existing state-of-the-art neural networks for point cloud classification, and that includes the PointNet, PointNet++, and PointCNN, and DGCN, And that also relates to the question by Chirac. Is that right? Yeah, because
yes,
we also use the graph-based neural networks. So I hope that answers the question.
Yeah.
So we actually compare different types of neural networks.
Yeah, and to tag in on that, on the methodology part, also during the experiments that we had, for which we performed 4, each time we changed some steps in how we want to validate it and how we prepared our data for it. So not only did we test with multiple neural networks, but we also tested with different methodologies, of which some were proposed by one of our mentors as well, Jesus Balado Frias. And some were proposed also as experiments that Esri has performed in the past. So we've also based our experiments on approaches that were already tested.
very good. Then a question by Dongyang Peng. Was your algorithm of machine learning from a library, or did you implement the algorithm yourself?
I could answer that. No, it was from a library. It would have been much too difficult to implement a deep learning algorithm in just 2.5 months. It's a lot of research, so we were just using other algorithms and seeing if they can work well for our application.
Yeah, it's also for the purpose that we wanted to do with the project. So we wanted to see how the machine learning that is available right now can face in a different environment based on a different location, because a lot of research has been done into imagery and also in the outdoors. So we wanted to focus more on how value can be added to the indoor and the point clouds. So because this was the main focus of our research, we opted not to implement it from scratch ourselves.
And talking about the indoors, Robert Foute asked, did you also take a look at the indoor parts in trains?
Well, so this is more of a question related to the data that we were provided. So from Remco Blunder, sorry, we got the data for Amersfoort Central Station, which we focused on during our project. And in the scan of this station, they opted not to go to the tracks because there was a lot of people traffic there, and in the stations it was less. So for privacy reasons, we do not yet have those parts. So as a consequence of not having it in the data, we have also not done research into how we can see it in the trains. But it is something that we could potentially pick up for a continuation or for future work on this project.
Very good. Well, then it's the final question. It's quite a long question by Edward Verbree, your supervisor again. You enrich point clouds with the semantics, but points are still points. What are your ideas about rich, smart point clouds? Will they have more value for the user above derived products like 3D voxels or the 3D LOD models? Brief answer, please.
Okay, so brief answer, it depends. It's
yeah, right.
Yeah, because it's data, it really depends on the application that you use it for. So for instance, for the asset management that we focused on as a potential added value, knowing which points are which object will probably have more value to the user than in which voxel it is. But if you just want to, for instance, if you want to make a 3D model of the whole scene, then having a voxel-based structure can potentially be way faster and way more efficient. So it really depends on the application.
Very good. Brief and concise answer to this final question. And this makes us conclude this session. And again, I will give you the applause, and I hope that the others will join me digitally. So a big applause to you for this very nice presentation and discussion.
Thank you.
You're very welcome. And then we move on to the next part in the program, the presentation by Sweko, 3D in a landscape of 2D registrations.
All right.
And I think Mels can press the button now.
I will do so.